signatures of galactic-scale outflows. Please start.
Thanks. My name is Guangtun. I'm a Hubble Fellow at Johns Hopkins University. I'm going to talk about outflows.
You cannot quite yet start because you need to be equipped with this.
Video recording, yes. Let's see. Thank you. Hello? Yes. Hello? Yes. Okay, I'm just going to hold this microphone. Okay, so I'm a Hubble Fellow at Johns Hopkins University, and I'm going to talk about outflows with the new Sloan 4 survey. The paper is of archive. If you type my first name, you can, the first one that pops out is the paper. Don't type my last name, there's too many. I only got about 10 minutes, so I'm going to focus on the most essential physics here. Very quickly, I want to just say there's a lot of reasons to study outflows, but I want to emphasize one of the motivations. Recent observations have revealed a large amount of metals in the circumglass medium. So I don't have time to give you a full review on the current status of the field. I just want to show you my small contributions to the field. What I'm showing you here is a composite image of quasi-absorber spectra as a function of absorber redshift. So this is observed wavelength. This is absorber redshift. And this diagonal line here is a magnitude-2 absorption line system. You can see it's actually a doublet. So this is from about redshift 0.4 to about redshift 2.3. So in Sloan, from Sloan 1 to 3, from DR12, I constructed a catalog about 100,000 magnitude-2 absorber systems. This is publicly available, so you can play with them by yourself. So these 100,000 absorbers, of course, indicate 100,000 gas halos. Most of the host galaxies cannot be seen because they're too faint, right? But there's another way to study circumglass medium, which is to start from the galaxies themselves. So what I'm showing you here is the amount of magnitude around so-called luminous red galaxies at redshift 0.55 from Sloan 3. So on small scales, the gas is associated with the host halos of LRGs themselves. So LRGs, they are mostly massive elliptic galaxies. And on larger scales, this is about 10 megaparsec. So on larger scales, the gas is associated with the so-called two-halo term with nearby galaxies. Okay, so magnesium, of course, is an alpha element. So it's a metal mostly produced by type 2 supernovae. So the question is, where did all these metals come from? So most of the time, we study circumglass medium using background sources. In this case, we have a background quasar, and we can see all these absorption lines induced by the circumglass medium, right? But we can also look at the galaxies themselves, because the photons from the galaxies themselves have to penetrate interstellar medium and the circumglass medium and a lot of other things to reach Earth. So this is where I want to introduce the new Sloan 4 EBOS survey. So EBOS is the BAO component in Sloan 4. It's the extended baryon oscillation spectroscopic survey, and it will cover the redshift range between 0.6 and 2.3, and the timeline is in a 6-year period starting last year. So EBOS is going to target 4 chasers to measure BAO at different redshifts. So I want to focus on this one. So this is so-called ELGs, emission-line galaxies. So emission-line galaxies, obviously, they have strong emission lines, and most of them are oxygen-2 emitters. So they are really faint, so it's very hard to detect them. So for cosmological purposes, we have conducted a series of pilot observations to see how feasible it is to get the redshifts of these emission-line galaxies. So what I'm showing you here is the composite image of the emission-line galaxy spectra from the pilot data. Again, this is observer frame wavelengths, and this is galaxy redshift. You can see all these emission lines. For example, here oxygen 3, H beta, and oxygen 2. You can also see some absorption lines here, right? Magnesium 2, iron 2 over here. So blue means the flux level is extremely low. So it's actually really hard to target these galaxies. But from the pilot observation, we show it could be done. So I'm going to stack all these spectra to show you what a typical ELG spectrum looks like. Of course, you can see all these emission lines, and they look just like a typical star-forming galaxies. I want to focus on this near UV coverage because now we are reaching redshift beyond 0.6. So we have near UV coverage. So if I normalize the continuum, you can see all these absorption lines. There's also some emission lines. I'm going to overplot a composite spectrum of the quasar absorbers, which is the red line. So we can identify all these absorption lines seen in both. So we have -1, -2, ion 2, ion 2, and so on and so forth. So these emission lines are in fact so-called non-resonant emission lines. This is ion 2. I'm going to explain it just a little bit because this is very important. So I'm going to zoom in again on this region. What I'm showing you again is the comparison between the composite spectrum of ELGs and the composite spectrum of quasar absorbers. So you can see, of course, the blue absorption lines from the ELGs, they're blue shifted. What this means, this is the outflow signatures, right? So what about these non-resonant emission lines? So these non-resonant emission lines are in fact pretty simple. So what I'm showing you here is the energy level diagram of the ground state of singly ionized ion and the first excited state of singly ionized ion. So this absorption line corresponds to the transition between the lowest level of the ground state and the lowest level of first excited state. Of course, the excited electron will want to come back, right, all the way to the lowest level. So there must be a lot of emission filling in on top of the absorption. But if you look at the J value here, the total angular momentum number here, so this is 9.5, this is 9.5, but this is 7.5, the second lowest level. So delta J is 1, which means the excited electron will also want to come back to the second lowest level. So this line corresponds to this emission. So this is non-resonant emission. Okay, and the other pair has the same story, but now it's the second lowest level of the excited state. Okay, so I don't have time to tell you the details, but I developed an outflow model that explains almost all the observations. So I just want to focus with the next few minutes. I just want to focus on two very interesting predictions of the model. So as I said, the excited electron will want to come back all the way to the lowest level. So there must be a lot of emission on top of this absorption. So how do we test this proposition? So I can compare the line ratios in different sources in the emission line galaxies and in quasar absorption line systems. So the model predicts. So the model predicts for the 8 absorption lines I have, there's more emission in infield for these lines, and if there's more emission infield, so the line ratio will be smaller in the emission line galaxies. So what I'm comparing here is the ratios of line ratios. Okay, so the trend is predicted by the model, and the symbols are the observed values. I also developed a method to correct the emission infield. So after the emission infield correction, what you are seeing is that the ratios of the line ratios in different sources are consistent with each other. Do I have another half minute?
Nearing the end.
Okay. I just want to say interpretation without correcting emission infield would be very wrong. Okay. So I just want to say one more point because this is so cool. I really want to show you. So the model also predict observed absorption velocity profiles for different lines. So blueness is more blue shifted, red is is less blue shifted. So this is the prediction from the model, and what do I observe? So this is the data. So magnesium 2 is more blue shifted, iron 2, for example, 2374 is less blue shifted. So this is predicted by the model, and this is data. I didn't do anything else. Okay, I just want to emphasize and interpretation without correcting emission infield would be wrong in this case. And also, this is pilot data. We haven't really started the survey yet. Okay, so in the future, we will have Bayesian PFAs. So we will have 22 million galaxies at a higher redshift, and I'm only using about 9,000 of them. And we can, in principle, answer a lot of ground questions in the future. So I'm going to stop here. Sorry, I went a little bit fast. Yes. Mm-hmm.
So any quick questions while the next speaker is setting up? So it looks like you're already getting good data, even on the pilot stage, and
Yeah.
it's amazing the amount of data that you'll be able to analyze.
Yeah, there will be 20 times more, yes.
So I just want to emphasize the importance of this because most of what we think we know about these outflow velocities comes from magnesium.
Yeah.
And all of those velocities are too high, as you
Yeah.
have shown. So this is great work. Thank you. Right.